In this module, we are going to talk about the foundations of chemistry that we're going to use through the rest of the course. Um, we're going to talk about atoms and their structure, then we're going to talk about the periodic table, and then ionic and covalent nomenclature. And nomenclature is just a fancy word for how to name things. So throughout this module, we're really going to learn the language of chemistry so that we can apply it to cosmetics later in the course. So let's dive into a little bit of history here. So let's talk about the atom. When we think about the atom, a lot of times we see pictures that look like this, or maybe we see pictures that look like this. And so we're going to jump in and we're going to go through a little bit of history about how we came about these sort of pictures that you've seen throughout your scientific career. Now, when we talk about this, we talk about the atomic theory of matter. There were Greek philosophers that believed that there were small particles, and they named these atoms, which just meant uncuttable, and they made up all of nature, right? And so experiments in the 18th and 19th centuries led to an organized atomic theory by John Dalton in the early 1800s. And so this is John Dalton. We don't have a photo of him, but we do have this sketch of him. And so here's kind of, he did a bunch of experiments, and here is what he came up with, right? He said all matter consists of tiny particles called atoms, right? And atoms cannot be created, divided, destroyed, right, or converted to any other type of atom. Atoms of a particular element have identical properties. Atoms of different elements have different properties. Atoms of different elements combine in a simple whole number ratio to produce compounds. Okay, and these are stable combinations of atoms. So, for example, water is H2O, where there are two hydrogens for every one oxygen. So those are whole number ratios. We have two entire atoms of hydrogen to one entire atom of oxygen. We don't have two atoms of hydrogen to 1.5 atoms of oxygen, right? So we've got these whole numbers ratio combinations. Okay. Then chemical change involves joining, separating, or rearranging atoms. Now, when we look at this, these are called postulates. They're just points, right, that he made. 1, 4, 5, and 6 are still regarded as true. 2 is not. Okay, so this is no longer true, and the reason that this is no longer true is now we have radiation. And we always had radiation. It's just now we know what radiation is, right? You've got to remember this is in the 1800s. And so we now know that what radiation is. We know that atoms can be divided. Okay. And then the other one that is no longer regarded as true is 3, right? And the reason this one is no longer regarded as true is because we discovered isotopes. Okay. And isotopes are going to have a different number of neutrons, and because they have a different number of neutrons, they aren't identical, right? So elements can have different numbers of neutrons. Those are called isotopes, and they're no longer identical. And we're going to talk about those as we progress through this chapter. So this was sort of the foundation of what the atom was in the 1800s. Now, what's pretty amazing here is that 4 of these postulates are still considered true. Which, given that was, about 250 years ago, that's pretty amazing. So let's talk about how different parts of the atom were discovered. All right. So J.J. Thomson came along, and so Eugene Goldstein He was a German physicist, and he was the first to discover that positively charged particles formed when electrons were removed from gas particles in a cathode ray tube. So when we look at a cathode ray tube, which we're going to talk about quite a bit, it's just a tube that looks like this. So we have a cathode and anode. Those are just two opposite ends of the tube here. The cathode has a negative charge. The anode has a positive charge. It is hooked up to electricity. Electricity runs through the tube here. That's a cathode tube. Okay. Now, Eugene Goldstein was very interested in the electrical discharge in vacuums. So they would vacuum out all the particles, and so that tube would be empty. There would be no gas particles. Now, his work suggested that there was the presence of a proton, which is a positively charged particle, but he didn't quite identify it as a proton, and so that positively charged particle was later discovered by Ernest Rutherford. But he was the first person to really find evidence of protons, but he's not credited with the discovery of the protons. Okay, now. So that was all using a cathode ray tube. Now, J.J. Thomson also did experiments on a cathode ray tube. And here's a photo of him. And his experiments were in 1897. And he identified these negatively charged particles that were emitted from an electrode in that same cathode ray tube, which is an evacuated glass tube with a cathode connected to the negative terminal of a power supply. So what he did, right, is we had electricity that was passed through the evacuated glass tube, and we had this stream of particles that was emitted from the cathode and traveled to the anode. So they were emitted here and they traveled there, right? When a magnet was held up, the particles were deflected with the magnetic field, right? So that indicated they were negatively charged. Now, so I want us to put some words to that. So the beam from the cathode ray is deflected towards a positively charged plate. Okay, so basically what happened is that if this is showing a magnet with a positive side or positive pole, and this beam was attracted to it, that indicated that this beam was negative. Okay, and so from this, he said, hey, look, right, atoms contain negatively charged particles. And we call these negatively charged particles electrons. Okay. Now, the other thing he did through some experiments is he figured out that these had a constant mass to charge ratio. Okay, and so when he figured out that these had a constant mass to charge ratio, and when we say a constant mass to charge ratio, it equaled one number. So it was 1.76 times 10 to the 8th coulombs, which is, it has a unit of C per gram. Okay. And so basically what could happen is if somebody could figure out the mass of an electron, then they could figure out the charge, or if they figured out the charge, they could figure out the mass, because we had a ratio here. And so Robert Millikan came along and performed oil drop experiments because he was interested in figuring out the mass of an electron. So he advanced Thomson's work by figuring out that mass of an electron. Basically what he did, right, is he had oil drops. These were created by an atomizer. They fell through a pinhole to a lower chamber here. Okay, and he was viewing these through a microscope. He had x-rays that ionized the gas molecules by removing the electrons, which were picked up then by the oil droplets. And he could adjust the electric field between the two charged plates. So there were two charged plates here. He could adjust that electric field, right? And since the mass of the droplets was known, then the charge of the droplets could be calculated. And so once that electron charge was known, the mass of electron could be calculated. So Robert Millikan determined the mass and charge of an electron with this oil drop experiment in 1909. And so we have the electron charge here, and then we have the mass of the electrons there. So he went on and discovered that. Now, so with all of this information, J.J. Thomson came up with a model for the electron, for the atom, and he called it the plum pudding model. Now, with the plum pudding model, this is a picture of plum pudding if you've never experienced plum pudding before. But basically what it is you have dough and then some sort of fruit that's distributed through this. This reminds me a lot of bread pudding. And so basically what he said this model is that there's an atom and there was positive charge that was distributed throughout the atom. And then there were electrons that were embedded throughout the atom here. So let's put some words to that. The plum pudding model has electrons distributed throughout diffuse, positively charged sphere. Okay, so that was the plum pudding model. We've got these electrons, they're distributed throughout this diffused, positively charged sphere. Now, right, this model didn't last very long because we basically discovered radioactivity, right? And so at the same time that we were looking at scientists were investigating these atoms, nuclear experimentation was also happening. So a few things to kind of keep in mind here. Henry Becquerel was a French physicist in about 1896, and he was investigating radiation that was released from pitchblende, which was a uranium ore. So what he discovered was radiation. And so he basically said, hey, look, some materials produce invisible radiation consisting of charged particles. Okay. Now, other people that were investigating this were Marie and Pierre Curie. They also showed that radiation consisted of small particles, right? And again, they were investigating a uranium ore, which is called pitchblende, and this is a picture of pitchblende. This is a picture of Marie Curie. And so through their experiments, they defined radioactivity. And so radioactivity is just defined as the spontaneous emission of high energy radiation and particles. And specifically, there were two particles that they looked at. One was beta particles. Beta particles a lot of times are represented with a Greek beta, like this. And these are basically just high energy electrons. And they also identified alpha particles, which are a lot of times shown with the lowercase Greek letter alpha. These have a +2 charge, right? And the mass of a helium nucleus. I did not spell correctly, so hold on. I got real excited there in my writing. There we go, nucleus. All right, so this information came out and was used by Ernest Rutherford. And so Ernest Rutherford set up really to validate the plum pudding model, okay? And so Rutherford, which there's a picture of him there, he was a physicist from New Zealand, right? Attempted to validate the plum pudding model by bombarding a gold foil with alpha particles from a radioactive source. Okay. And so basically what he did is he had an alpha emitter. So this was a material that emitted alpha particles. And he shot it at a really thin layer of gold foil. Okay. And if the plum pudding model was correct, then what he expected to happen was that these alpha particles, which are shown here with these black lines, would pass all the way through. Okay, so this model right here is that plum pudding model, right? And if that positive charge was really super diffuse, then these would pass through. These positive particles would pass through. But instead what happened, right, is that he did get some positive particles that passed through, but he had some positive particles that were deflected. Now, what that means is basically they bounced back, right? So they would bounce over here and they'd bounce over here, and some even bounced back directly to the source here. And that was wild to him. He described it there in one of the accounts. It says he described it as if he had shot a shotgun at a piece of tissue paper and the pellets bounced back. That's how shocked they were. So because we had these positive charges that were bouncing back, what he hypothesized was that there is a solid center of the atom that contains positive charge. And so when these positive particles hit it, they were deflected because positive things repel each other, right? So his experiment disproved the plum pudding model. So that told us that the nucleus had a concentrated region of positive charge. So this experiment told us that the nucleus has a concentrated region of positive charge. Okay, that's what we know. So far in our journey in the atom, we have an electron that's negatively charged, and then we've got a proton that is positively charged. There's one more piece, which is a neutron, right? The neutron was discovered by James Chadwick. He was an English physicist, and he bombarded a thin sheet of beryllium. So we've got that same kind of alpha source. We have a thin sheet of beryllium now instead of gold with alpha particles. When he did that, a high energy radiation was emitted by the metal that was not deflected by either electric or magnetic fields. So we've got this high energy radiation that's not attracted or repelled or anything by fields that are positively or negatively charged. Okay, so he concluded that radiation consisted of a third type of subatomic particle, which he named neutrons, because they were electrically neutral. Okay, so now we have the nuclear atom. So when we talk about the nuclear atom, and the what we recognize today as our atomic nuclear theory here is that we have a nucleus, okay? And in the nucleus, we have protons and neutrons. Protons are positively charged. Subatomic particle. And neutrons are electrically neutral. Okay, and both of these are found inside the nucleus. Okay, now outside the nucleus are electrons. So electrons are outside the nucleus. Right, and these are negatively charged. Okay, so when we look at this, if we're looking at a gold atom, right, gold atoms are around 288 picometers, okay, and the nucleus is about 0.01 picometers. So the nucleus is very small, right? This is where the protons and neutrons are, and the electrons are found in the space around the nucleus. So the nucleus itself doesn't take up very much space. The area where the electrons can be found is very large compared to that nucleus here. A really good analogy of this is if you go to a professional football stadium, and this would be the football, right? The nucleus would be about the size of the football, and the rest of the stands would be kind of the rest of the space where the electrons can be. So that's a really nice size differential there. So just in summary of everything we've learned, right, here is a summary table. We have an electron. Electrons can sometimes be shown with the symbol E minus. They have a -1 charge. Here is their approximate mass in both grams and atomic mass units. We have a proton. Sometimes these can be shown with a P plus. Here is the charge. Here is its a approximate mass and atomic mass units. Here's a neutron. Right, there's its charge and there's its mass. Do not memorize these numbers right here. Basically, what you need to know from this is a proton and neutron have about the same mass, and electrons are much, much smaller. That's it. That's all you need to know. You do need to know these charges. Okay. So that summarizes our nuclear atom and the history about how we got there. In the next screencast, we are going to talk about isotopes and ions.